So here is a summary map of the first lecture on classic feature representation methods. So first, we're going to start out with a brief overview of typical conventional supervised regression and classification problems and how we map them into matrices and have a beautiful algebraic representation of that. So this is the whole map, and we're going to go over that quickly. So this is just, as I said, an overview of what we have seen in detail in the previous lecture. So it gives you a beautiful algebraic representation of the whole lecture, different parts, including supervised regression, linear and nonlinear models, and also classification, supervised classification, fixed spanning sets and learnable spanning sets, representation learning, and generalized matrix factorization. So let's start with the first part. So here, you guys can see that supervised regression problems can easily be formalized as a weight learning problem. So the goal is for us to learn how to optimize this loss function. So for now, as I mentioned earlier, we just define the loss. So I'm not going to go into details and say, oh, how are we going to optimize this loss? So we will see that in the coming lectures. But for now, let's focus only on this single regression model. So the goal is to learn the weight vector, and this weight vector D right here, right? So that's what we're after. So we want to learn a D plus one dimensional vector that allows us to predict the final Y. So this is, how we represent it. So the goal is to minimize the distance between xi transpose y. So xi transpose here is actually this vector. So for example, this is the vector xi. So when we multiply it, the transpose of each sample, so it has D plus one features. As you guys remember, D is the number of features, right? And one is actually the bias. I'm going to make this smaller, sorry. So yeah, so D is the number of features and one is for the bias. And when you multiply by this D plus one mapping vector, so this is our mapping, function, right, that we want to learn, we can predict y hat. So this will be our y hat right here. So this is what we predict. And this y hat basically gives us the score for each of our n samples over there. Okay, so now the loss function is simply formalized as an L2 distance, a squared Euclidean distance between the y predicted vector and the ground truth one. So here for our n training samples. So these are the training samples encoded in our matrix X tilde. So we called it X tilde because it's a compact form, which means the first feature right here for each sample is set to 1, and that is to account for the bias W0 here, and we have basically W1 until WD. So from W1 through to WD, and this is, what we are after. So we want to learn that, and also we want to learn the bias that we will assign to the data. Okay, you guys can see that this is, a simple formalization, and you can turn this matrix beautifully and this linear algebra, turn it into what we call a computational graph. So you can model this graphically. So you can write down, y I hat is the summation from I equals to 0 to D, right, of WI, and you have X, let's call it, so I'm going to use another index here, J. Actually, it should be that way. So like I, and then we have so XI, and so J, so I need to put here, J actually is the, we're looping over this part, okay? So that we're reading the feature values of sample I. So I is actually the sample, okay? So this is our sample I that we want to predict its score. And then our goal is to learn the feature, the W for each, feature. So WJ here you guys can see how I corrected that. So you need to make sure that your math is consistent and it works perfectly well, right? So it's good to always make kind of these tiny mistakes, because then you get to check and see, you know, like, does it make sense? What am I actually multiplying here? All right. So you can write this down as that. So plus, so here we have, you know, the first element. You can consider this as xi, small xi tilde 0. So this is xi 0. And so that's if I'm going to include it in the equation. Or you can alternatively write it in a different way, which is, you know, starting from actually 1, okay? And tilde, so the index of j starts with actually 1. You guys can see it here from 1 to d, right? And then we need to add the w0, right, times this. So you guys can see that this is the formula and how we can simply turn a computational graph into our, you know, into a simple multiplication of scalar values, all right, and vectors. And here, this is exactly the formula that we have in a compact algebraic form, xi transpose w. So you can also write it this way. So if you write it in the compact form, you're going to have xi transpose tilde, right, and w. So this is exactly our, you know, like the form of this, you know, explicit expression. All right, cool. So now we can see that a linear regression, a simple linear regression problem, is coded into this, you know, w that we want to estimate. So we want to learn the w that is that lives in a d+1 dimensional space. So what's fascinating about this, right? So I want to take a moment and look at this, right? Just for a moment. What is fascinating to me that this w right here, okay, it captures, you know, it captures the full mapping of all diverse samples, every single sample here that has different values. I can map each one of those samples one by one, okay? So I can map each one of those to a completely different value. So if you're predicting, for example, the age of the picture, you have a picture of a dog here, okay, and you have multiple dogs, and you want to predict the age of the dog based on the picture, right? What is fascinating is that this mapping, this w that we're after, it captures everything, and it captures the diversity. So it maps every single dog picture that you have into its expected age. And if your learning of the w is very good, is very optimal and accurate, then you're going to have a very good prediction. So everything basically in regression boils down to learning this vector. Now, if we generalize this to multiple regressions, so we have seen multi-regressions and in this formalization, so let me just remove this. So what we have also, you know, the data. So our data, original data, is represented in this matrix, right? X tilde with the bias, so it's a compact form. We have n samples times d features plus an additional, you know, like value 1 that we add for, as I mentioned earlier, for the bias. And then we have multiple output scores. So here and now, we are predicting a matrix, a transformation matrix, a weight matrix, okay? And actually, this weight matrix is a transformation matrix of my feature. It's a feature transformation matrix. So we're transforming the features, okay? And then we have C values. So for each one of those, we have W1, all right, until WC. And each of these vectors will allow me to map, you know, so let's take vector 1, right? So this allows me to map each of my samples into an output vector here. So the number of samples here, and this is the output 1, and then I have C outputs. So I'm predicting a matrix of scores for every single type of output that I'm targeting. For example, here, I detect age. Here I detect, for example, size or whatever. It could be anything, okay? So this is beautifully written in a compact form. And our goal, of course, is to predict, is to minimize, to predict a y hat. And ideally, this y hat will satisfy a minimal distance to y. Ideally, we would have y hat matrix almost equal to y, all right? So this is how we write it down. We can also write it as a summation over all these, linear regressors that we have. So each of one of them is a linear regressor because we have a linear model here through this matrix projection onto this WC, right? And then we're trying to minimize the squared norm across all of these. So now what you can do, you can write this down as a computational graph. So what I'm going to do, guys, I would like you to take a minute, okay? So write this down, and I want you to express it as a computational graph. And here is, so this is a graphical notation of the first one. So the first one, basically, we have only one score. Now, I want you to add multiple scores. Okay, so we're going to add multiple scores. So I'm just going to scribble this quickly. So now we have many scores, C scores until WC. And we're going to predict, sorry, we have, C scores. So we have multiple mappings. So C, W vectors to learn, C mappings or transformations to learn for every single target score. All right. So let's take a minute and try to create the graphical representation for that. And remember, these are very important, the dimensions. So make sure that you put the right dimensions and express, two different outputs. So what I want you to do is to express two different outputs. So yi hat and yj hat. So let's say you have two generic outputs. And if you can do it for that, then you almost solve this for the rest of the scores, okay? So let's look at the solution together. So here it is. So basically, if I have, two outputs, right? So this is, the first output for my sample I. So by the way, this is a single sample. So I take a single sample. So this is one single image, for example. This is my sample, and each of those represents the feature values for each of those samples, okay? Is for each element or entry in that sample. Okay, so we have different D features. And basically here, you can write this down as you have multiple summations, right? So you're first predicting the first score, the score 1, as a linear combination. So let's take a different, as a linear combination of all of these elements. So here, so you take the bias, and then you take every single one of those, and then you do a linear combination, and it gives you the predicted final score, all right? And then for the second score, for the score C, right, it's also defined as a linear combination of each of these features of my sample I, all right? So that's how you express it, and this is exactly, the translation, the translation of this equation, which is basically x, if I write it down, x tilde w, sorry, so w is equal to y hat matrix. All right, cool. So this is how we express it. And then as a small network, okay? So now it becomes a neural network when we do other things like, back propagation and training, but this is just a simple network that we're trying, a simple, we can call it feed-forward network that allows us to predict these multiple values, and we can have many values right here. All right, cool. So now let me just go forward and give you an example. So let's look at an example. So let's say we have a d-dimensional, we have a one-dimensional point, so belongs to R, and this point has, the y belongs to R2. So we have two basically values. So we have y1, okay, and y2, and this is for each sample I. So this is my vector that has two values. So when we say solving a multilinear regression problem, it means the first y1 score can fit into this distribution, and the second one, we're going to use a different color. We have something like this. Okay, so when we have multi-linear regression problem, it means my first W, the W is called the W1 that will predict. So let's choose a different color. So the W1 will predict this line. So this is these are the parameters of my linear model. Okay, and then the W2 will predict this. So basically, this is, if we write it down properly, this is X, tilde transpose W1, okay, of this, for example. And this is, the line here is X transpose, okay, W2. So if we have a second, for example, W2, all right. And you guys can see that beautifully using this matrix. Also, again, while giving a single sample X, so let's look at a single sample X, this X right here, this value, for example, 2.8, I can easily see that this is the real value, the ground truth value of Y1, and this is, for example, Y2, right? And when I project them onto the line, because my line is really good, so when I do projection, I find this projection. So this is the Y1 hat. Okay, so that's the value. And this is when I project this point right here onto this line, I have here the Y2 hat predictions. And the error, the mistake that I've made, because this point is actually very close, it's actually too small. That's my residual mistake. It's actually very, very tiny. And if you take other points like this one, then we have a larger mistake here. Okay, so with respect to the model. So what is fascinating, again, that in multi-regression models, and we have a linear case here, so supervised regression linear, that once we get this matrix, right, we can predict any kind of set of scores, right? We can predict everything. So we can map one single subject onto a set of multiple scores right here. So these are the scores that I predicted sample I for this sample xi using these mapping functions or this mapping matrix W, feature transformation matrix, okay? And this happens for every single sample. So I'm using a fixed learned optimal W, and we will learn how to estimate this, how to minimize, L over W, the variable of the loss later on. But if we get a very good W, then we can predict all scores of any kind of input feature, sample. All right, cool. So now quickly, I'm going to go quickly over this. So for nonlinear mapping, it's actually very easy. So we will see it's the same thing. So basically, instead of having a simple linear model, now we have a nonlinear model. We have a transformation Fi that is a nonlinear transformation. And it's the same formalization. Basically, guys, you replace the X tilde with F tilde, which is basically the transformed features. Okay, so here I'm going to write it transformed features. Okay, and it's a nonlinear transform. So we use a nonlinear transformation, and we also are allowed to change the dimension. So we go from D to B. Okay, so we have B basis here. So B, it's a new space. So our new space is spanned by B vectors or B dimensions. So we are not living into the space, the D-dimensional space anymore. So when you transform the data using, a particular feature transformation matrix or function, you're able to get a transformed representation of the data with the new feature values right here. And you don't have necessarily the same number of features. Of course, B could be equal to D, which means I don't have any loss of information. But if we have B, smaller than D, then we will have some loss of information because my original vector now is represented into a lower dimensional space. okay? So this space, basically, it's the same thing. So once we transform, we have the transformed representation of each sample I. We learn a mapping vector W, and it allows us to predict the Y hat right here. And ideally, the Y hat will be almost equal to Y, which is the ground truth observation for every single sample of my training and samples. All right, cool. Now, if we look at this, how we have seen that if it happens that you have a good transformation. So let's look at this. So we have, for example, this kind of distribution. All right. And this is my X right here, and this is my Y. And you guys can see that this is a nonlinear relationship between the X and the Y. So if I want to fit a model, it will be something like this, like a parabola. So let's say I can have a good guess at this, F. So I know that I'm transforming, I'm writing something of this form, which means F of X is equal to ax squared plus bx plus c. These are the hyperparameters that I want to learn. So my w will be equal, because it's d plus 1, so it will be equal to the bias w0 plus a, b, c. Okay, so these are the parameters of the model. And then once, if we find this, if we have a good guess at F, so this is what we discovered last time. If I have a good guess, a good feeling about the shape of X, the shape of the relationship between my input data and output data, we can easily have, transform the data into a new space. Okay, so if we represent the data into the new representation, feature representation. So this is the new feature representation of my point X, so the new transformed features, and I have Y. What we're going to discover, interestingly, that now we have a sort of a linear relationship in this transformed space. So if I am able to learn F properly, what we're going to get is a beautiful space where we can easily now use a linear model to kind of solve this problem. And this is the power of learning the right transformation. So what we have seen that before is that we can have a guess, but this space can be way more complex. So we cannot always guess this, right? So that's the real problem that we have in machine learning. If we were able to guess the shape, then we can solve it right away. But the problem is that the F, in most cases, is unknown, and we cannot actually see the shape of F, the transformation that we want. So we need to kind of learn it, and then using optimization and using a new formalization. Okay, cool. So that's that. Now for the multilinear regression, so you guys can see it's the same thing. So now we have multiple scores, the same thing. So I'm just going to go quickly over this. So the idea is that I have a different, like a nonlinear relationship. So let's say a first parabola. This is the first, output score. This is the second output score. So this is Y2 and this is Y1. All right. And then here we have X, and we have two outputs, right, guys? So we have X and we have Y1, Y2 as outputs. And if I fit a model, you're gonna see that I fit two parabolas. So I can use actually two fitting models here. And then this is, the first model that I fitted. So W1 and W, so you have WC. So including the models like the F1 and FC for each of those, right? So we're estimating the internal parameters, but also the F parameters, what's inside of the transformation. And if my F is really good, so we're going to have the same thing. We're going to have a linear relationship between the inputs. So this is F1, if we write it down. So we have F1 of X of the first features. And then if we do F2 of X, and here we have the output, okay, Y1, Y2, right? And you guys can see that we can easily fit a linear model. So, okay, so these are like very big, but it's fine. So something like that. All right, cool. So that's how we do it. Right? Good. Now, for classification is actually very similar. So we have seen linear classification. So we use a simple, loss function here. So we project the sample onto the hyperplane. But the key idea about linear classification is that now that we have, for example, two features, right? So we have feature 1. So now we live in the feature space, and feature 2, and the predicted label is actually the sign of the of the point that we have, so in this space. So once we have, for example, different points, so this is class 1, this is class 2, and if I want to learn a linear model that separates these, so I have my linear model over here, and this linear model, its equation is actually X transpose W equals to 0, right? And then the sign of any point above this will be 1, and any point that is below will be -1, for example, for SVM. So what we're doing actually in classification, we are coloring or labeling the space. So we're labeling the whole space, and any testing point that will appear here will be, assigned a -1 or colored as blue. And any testing point that appears there will have a sign, for example, of 1. So this is the softmax loss that we have seen. And as I mentioned earlier, if you guys are interested in learning about how we actually even define this, what's the intuition behind the log and the exponential and the dot product here and multiplying by the y, you can watch the machine learning blanks playlist. And I think in lecture 5 or 6, we go over this in detail. And this is, a foundational lecture on machine learning. All right. So now when we have nonlinear classifier, it means it's the same thing. So instead of, we replace simply the X tilde with F tilde, and then we have the same kind of loss. And if we map this, if we draw an example right here, we have each point X having two features, X1 and X2, belonging to R2. So we represent our points like crosses right here and circles over there. But it happens that now we do have a nonlinear model. So for example, we can have even a more complex shape, like, all crosses will be inside and all circles outside. So this will be my model right here. Okay, so that we're after. So this is my nonlinear model shape that if I learn well, I'm going to get F tilde transpose W. All right, cool. So that's that with supervised learning. So we've seen all these, and by the way, guys, you can also represent this using linear algebra, and you can also do it using small computational graphs. Same thing. Okay, cool.